Hello everyone. So we will begin our mineralogy course from today. Now, as we all know, we are well aware that mineralogy is composed of three different subdomains. If you follow any standard book, the normal standard books, they start with descriptive mineralogy, then they move on to crystallography, and in the end, they go on explaining optical mineralogy. What we will follow in our course is that we will start with crystallography. Why? Because crystallography puts up a base for optical mineralogy and descriptive mineralogy. After we are done with crystallography, we will move on to optical mineralogy, and then in the end, we will study descriptive mineralogy. Okay, so all the minerals, their properties would be dealt at the later stages. This would be very helpful. Why? Because after mineralogy, we will start with the petrologies. And once we are done with all the minerals, we would have a base for the specific petrology, such as igneous petrology, metamorphic petrology. So, for example, olivine would be dealt in the later chapters. Now, that would be directly beneficial in igneous petrology classes. So, this mineralogy course would be very exhaustive. We will study each and every mineral so that when we go on to discuss petrology, we have a very solid base. Okay, and after you are done with this mineralogy course, you should have a very solid foundation for mineral science as well. So you would be able to deal with all the mineralogy questions that come up in your examinations. So now let us begin with crystallography. Okay, so this is the first subdomain of mineralogy that we will study. Now, before we go on to study crystallography, as you people must have studied in your colleges, I would like to discuss a concept that is known as symmetry. Now, symmetry, when I talk about symmetry, when you hear the word symmetry, it is a very intuitive concept. Okay, in your heart, you know what is symmetry. But if I ask you, can you define symmetry, then that would be very difficult. When you look at a flower which has a radial symmetry going on, you can see the symmetry, it pleases your eye, and you are able to say, yes, there is some symmetry in this flower, but you are not able to put them into words. So in this lecture, we will try to figure out how do we define symmetry. And this would be very important. Why? Because in the later crystallography chapters, you will see that crystallography is nothing but the study of symmetry in crystals or minerals, if you will. So now let us look at these two images. Now this is image 1 and this is image 2. Any Game of Thrones fans must be aware of that these are two flags of the House Bolton and House Stark. Okay, if you're not familiar with Game of Thrones, then also it doesn't matter for this class. Now let us look at the first image. In the first image, what do you see? You see a flag. You see a flag which has an outward appearance. Now this is the outward appearance. Now I want you to forget about anything in this flag except the outer appearance. So what I wish to do is that you just focus upon this part of the flag. Do you see some symmetry? Can you see? Okay, yes, this part is very symmetrical to this part. Or if you will, you don't see any symmetry, then that is also fine. If you don't see symmetry, and if you see symmetry, we will discuss it. Now let us imagine this yellow line. Let us imagine that this is the mirror plane. Now, do you see any kind of symmetry in this image? I can see a symmetry. Why? Because this part of the image, the left part, is an exact replica of the right part. And replica in which manner? When you look at a mirror in your house, okay, we are very well aware how mirrors work because for our entire life we see mirrors in our homes and offices and all. So mirror, what it does is it takes you and creates an exact carbon copy at the other side of the mirror. So you have an exact replica on the other side. So the left part of the image is an exact replica of the right part of the image, and you can imagine a mirror plane going through this flag. Is there a mirror plane in this direction? No, there is not a mirror plane in this direction. Why? Because if you look at this tip of the flag, this tip of the flag is missing at the top. So if there would have been a mirror plane here, you should see, if there would have been a mirror plane here, you should see a copy of this tip at the top as well. But you don't see that. So there is no mirror plane in this direction. There is only one mirror plane in this direction. Okay. Now let us move on. Let us look at the first image. Now let us focus upon this X. So there is an X in this image. Can you think of any symmetry that is present in this X? Yes, if you look at the first mirror that we talked about, this mirror exists. Why? Because this part of the X is an exact replica of this part, right? So you can imagine a mirror plane going here. Can you imagine another mirror plane in this direction? Oh, sorry, in this image. There is another mirror plane in this image. If you can imagine this direction, there is another mirror plane for this X. Why? Because the top part of this X is an exact replica of the bottom part of the X. So what we have seen right now, that the flag itself has one mirror plane. The X has at least two mirror planes. Now let us look at the third element in this flag. So we have an upside down human body. And we know that humans are bipedal. They have bipedal symmetry. What this means? This means that if you take a human being, if you take me for suppose, or if you take yourself, if you cut through in between, the outer appearance of us is an exact replica. The left part of us, the exterior left, is an exact replica of the right side. Okay, so we have a bipedal symmetry. That means we have a mirror plane going through us. The external skin and external parts of us have a bipedal symmetry, not the internal organs. Why? Because I have a heart on my left, I do not have a heart on my right. So internally we don't have any symmetry, but if you look from the outside, a human being has a bipedal symmetry. Do you see that bipedal symmetry here? Yes. If you imagine this mirror plane again, you can see that this left hand has a replica to the right. This foot has a replica here as well. So the human being also has a mirror plane. Now, does the human being have a mirror plane in this direction? No, it does not have it. Why? Because you have hands here and you have legs here. If this mirror plane would have been in the picture, you would have seen a hand here and a hand here as well, which you don't see. So this mirror plane does not exist, while this mirror plane exists for the human part of the image. So the backside had one mirror plane, the X had at least two mirror planes, and the human being has one mirror plane. So now the question is, when you look at the image as a whole, how many mirror planes are in this picture? The answer is, you have only one mirror plane. You don't have two mirror planes. Why? Because this X is part of that picture. Now the X in itself has two mirror planes. But when you combine the X with the human being and the flag, the image in total only possesses a single mirror plane. Okay, so whenever you talk about symmetry, for example, we are talking about mirror plane symmetry. If a part of the image has some symmetry, it does not mean the entire image will have that symmetry. You have to take in the entire image itself and then look for the symmetry that is present. You cannot say that the X part has this symmetry, so the entire image will have. No. The X is part of the entire image. So the entire image should have the symmetry. If you want to talk about the symmetry of the entire image, you will have to look at all the sub-objects. For example, we have three sub-objects in this image, the X, the human being, and the flag. Whatever symmetry combined they have, that is the symmetry of the entire image. So the entire flag has only one mirror plane, and the mirror plane is something like this. We will build upon this concept when we look at the second image. Now let us look at image 2. Do you see the flag in image 2? So the flag in image 2 is something like this. But there is an additional point. It has two colors. Okay, so it has a green color at the top and a off-white color at the bottom. Do you see any symmetry? Yes, you can imagine that there is a mirror plane here. Why? Because the left part is a exact copy of the right part. Do you see a mirror plane here? No, you don't see. Why? Because first of all, this tip is missing at the top. Also, the color scheme is also missing. You have a green bar at the top. You don't have a green bar at the bottom. So this flag image also has a single mirror plane, and that mirror plane is in the north-south direction. Now let us look at the other part of this image. So we have this wolf symbol in this. Now does this wolf symbol have any kind of symmetry? Can you see any kind of symmetry? No, you don't see any kind of symmetry. Why? Because if you imagine this mirror plane, this mouth of the wolf is absent here. You have the mouth in the right, it is absent in the left. So this north-south mirror plane is not part of this wolf. Do you have a mirror plane here? You don't have. Why? Because you have an eye here. The eye is missing here. Do you have a mirror plane here? No, you don't have. Why? Because you have this neck of the wolf here. It is missing at the top. So this wolf, the wolf part of this flag has no symmetry. I cannot see any symmetry. My eye is not able to figure out any symmetry for this wolf. While the flag itself, the back of the flag had a mirror plane. Now the question is, does this image in its entirety have any symmetry going on? The answer is no. This image in its entirety has no symmetry. Why? Because this wolf is part of this entire image. Now because the wolf possesses no symmetry, even though the backside of the flag has a mirror plane, the image in total is combined of the wolf plus the flag, which has no symmetry. This one had symmetry. Why? Because the flag, the human being, and the X, they, when combined together, still had this mirror plane going on for them. So whenever you talk about symmetry, you would have to look at the entire object. You cannot say, I will look at a part of the object, okay, and judge for symmetry. To judge for symmetry, you have to look at the entire object, and then we can talk about whether a symmetry is present or is absent. So we have talked about this. We have already talked about it. Is a very intuitive concept. Even when you looked at this wolf, intuitively you knew that there is no symmetry going on. When you looked at this human being, you intuitively knew that there is some kind of symmetry. We talked about what kind of symmetry? A mirror plane symmetry. So symmetry is a very intuitive concept. Let us look at this example. If we take this flower, can you see any kind of symmetry in this flower? If you take this petal, now this petal has multiple copies. So this petal also, each and every petal that you see is an exact copy, not an exact copy, but a good copy of the first petal that we see. So all these petals, they are exact carbon copy, not exact, they are copies of the initial petal we see. And you can imagine, yes, there is some kind of a rotational symmetry. Some kind of a rotational symmetry going on. Rotational symmetry means that there is some kind of axis along which this flower petal is rotating, and it is kind of symmetry. And we see this these kind of symmetry in our day-to-day lives. Whenever you look at a flower, you are able to intuitively decipher, yes, there is some kind of symmetry in this. And what kind of symmetry we are talking about? We are talking about a rotational symmetry. Intuitively, we also know that yes, there is some kind of rotation going on. This flower petal is rotating and pasting itself along the axis which rotates. Now let us look at this image. Can you figure out any kind of symmetry in this image? Now it is a tough one. It is a tough one to define what kind of symmetry. For example, in this we knew some kind of rotation is going on. In this, there is some kind of rotation going on. What is that rotation? This yellow square has a copy here. This gray square has a copy here. This inverted S has a copy here. So we can imagine, yes, there is some kind of rotational symmetry going on. There is something, some kind of rotation, not a rotation in such a manner, but yes, this gray has a copy here. This gray part has a copy here. This yellow part has a copy here. This F also has a copy here. So there is some kind of symmetry going on. And we are able to see it. Intuitively, we are able to see it. We may not be able to define it, yes, what kind of symmetry this is, but intuitively we see, yes, there is some symmetry going. So this was the motive of these things. The motive was that, yes, we are able to see symmetry, but how do we define that? How do we scientifically define what exactly symmetry is? So what is symmetry? Symmetry is nothing but an operation. Operation is something that operation is nothing but you take an object and you move it. Okay. So for example, in the flower petal, you took the first petal and you moved the petal in this location. So operation is nothing. Operation is moving something, copying something, pasting something. So symmetry is defined in such a manner that when you are done with this operation, when you are done with rotating or copying, pasting, the final object that you get, should be exactly same as the initial object. Exactly same means that it should coincide. Coincide means that the position, the initial position that you started from and the initial orientation you started from is exactly the same as the final position and orientation you are at. Okay. I know that it is a lot to take in. So we will look at some animations so that we are able to better understand these concepts. So for symmetry, what was the case? You started with an initial object. You had an initial object which had some orientation and some position. You did the symmetry operation and you land up with a final object. The final object also has some orientation and position. Now when these two orientation and position exactly coincide with this orientation and position, that means the symmetry operation that you did actually existed. If these do not overlap, if the initial object does not overlap with the final object, that means the symmetry element that you're talking about does not exist in the image. Now let us look at this square. Okay, so this square, we have a red square. Behind the red square, we have a green square as well. Now the green square is our initial object. Let us have a look. Okay, so we have a green square behind it. And the green square is not rotating. Why it is not rotating? Because the green square marks the initial object, the initial orientation and position that we started with. And this is the red square that would appear as the final object. Now what I will do, I will imagine an axis going inside the square, which is rotating the square. Okay, so the symmetry object that we are talking about, what is that symmetry object? That symmetry object is rotation. Rotation along our axis. Okay, for example, if you take this pen and this is the axis of rotation, what it will do, it will take an object and rotate it in such a manner. If this is the axis of rotation that you're talking about, it will rotate in such a manner. So we have imagined an axis going inside the square, which will rotate the square. Now we started with the green square. If after rotation, the final object that is represented by the red square exactly coincides with the initial object, that means the rotation element or the rotation symmetry element that we are talking about exists. If these don't overlap, that means the symmetry object that you were talking about does not exist in the image. Do they overlap? Yes, they overlap. So the rotation symmetry that we talked about for this red square does exist. What about the red rectangle? Okay. The red rectangle also overlaps with the green rectangle. That means the green rectangle was the initial object, orientation and position. When you did the rotation, the red rectangle or the final object exactly coincided with the initial object. That means whatever rotation you are talking about does exist in this image. Okay, let us take this example. So the green objects are the initial position and orientation of the object, and the red one are the final position and orientation. Now let us see what happens if we rotate it. So these are the rotation axes. The rotation axes are going inside the object and they are rotating in such a manner. What happened for the hexagon? For the hexagon, the final object is exactly equal to the initial object. Initial object. That means both of them overlapped. What happened with the triangle? The final object did not overlap with the initial object. Now, because the final object is not overlapping with the initial object, this means that this triangle does not possess this symmetry. What kind of symmetry? Rotational symmetry that we use to rotate it. So this example demonstrates the fact that if you have a symmetry, the final object should be exactly overlapping the initial object. Now in the case of the triangle, they do not overlap. This means that this triangle did not possess this symmetry, while this hexagon did possess it. Okay. This square possessed this rotation, this rectangle possessed this rotation, this hexagon did not. And this hexagon did possess it. This triangle did not possess that rotational symmetry. Now let us look at this example. So we are starting with a yellow triangle, and let us look at the animation. Okay, so this is the final part of the animation that we see. We started with this triangle, and in the end we had these 4 triangles. Now can you try to imagine where is the rotation axis in this diagram? The rotation axis is in the center. It is not in the center of the triangle. It is in the center of the group of these 4 triangles. Okay. In the last 2 examples, for example, the hexagon, where was the symmetry axis? It was inside the hexagon. Now it is outside this group of triangles, not inside any one of them. So this is not the case. The rotation symmetry is here. Okay. Now why is this important? Let us have a look once again. If you look at the final image, can you imagine that this has a symmetry going on for itself? Yes, intuitively we know that there is some kind of symmetry. This rectangle, this triangle is a copy of these 3 triangles. So there must be some kind of a symmetry going on. And we have already talked about where is the symmetry. The symmetry axis is inside this, outside these triangles, inside the group of these 4 triangles. Now, why is the position of this symmetry axis important? Earlier, in the earlier example, we saw that the triangle did not possess this kind of rotational symmetry. Okay. But now we are able to see now we are saying that through our eyes we can decipher that these triangles have some kind of symmetry going on. Now what is the difference? The difference is in the position of the symmetry axis. In this image, the object, that means the final object or the initial object that we talk about. What is the object in this image? The object in this image is the group of these 4. The object is group of 4 triangles. Why is it a group of 4 triangles? Because generally speaking in crystallography, whenever we talk about any symmetry, the symmetry operation should be inside the object. So whenever you look at any image, if you're talking about any symmetry operation, the symmetry operation should be inside the object. If you look at this image, the rotation symmetry is not inside any of the triangle, but is exactly at the center of this group of 4 triangles. So what becomes the object in this animation? The object becomes the group of 4 triangles. What was the object in this diagram? The object was a single triangle, a single hexagon. Now, why is this definition of object important? Because in crystallography, the symmetry element is defined in such a manner that it passes through the center of the object. Okay? You cannot, if you want to study this rotation symmetry that is present here, you would have to imagine a bigger object in whose center this rotation symmetry lies. If you want to study this individual triangle, you cannot study this individual triangle using this rotation symmetry. Why? Because this rotation symmetry is not inside this triangle, it is outside that triangle. So in crystallography, generally speaking, the object that you are talking about, the object for which you look at the final position and orientation and compare it to the initial position and orientation, this object is what? This object should be in such a manner that the symmetry element that you are talking about is at the center of the object. Here the symmetry element was at the center of the object. So the triangle became the object, and you looked for the initial position and final position of the triangle itself. Now in this image, the rotational symmetry is present here. So the object is a sum of these four triangles. Okay. So if you want to judge whether this object has any symmetry going on for it, the initial position and orientation, you would have to check for the group of four triangles. Why? Because the group of four triangles is defined as the object. Because the rotational symmetry is inside the group of these four. So you would have to be very careful when you talk about symmetry axis or symmetry operations. The symmetry operation should be inside the object that you are talking about. If it is not inside the object, then that is not the object. If it is outside the object that you're looking, that means in reality, you are not looking at the object. You would have to look at a bigger picture. In this image, that bigger picture is this group of four triangles. Okay, I hope that is clear. So what is symmetry? Symmetry is any operation, any movement that when you carry out, the object, the final object should coincide with the initial object. And the object is defined in such a manner that the symmetry that you're talking about passes through the center of the object itself. I hope that is clear. Okay, so we will continue with elements of symmetry in the next class.